Okay, this lesson is going to be chapter 9, but before I start that, I did revise the homework some, so let me just tell you for chapter 8 how I revised it. Got an announcement, maybe, for homework on Canvas as well, so hopefully you've already seen that it's revised. But just in case, let me tell you, chapter 8, I revised it. So for set A, you're doing numbers 1, 5, and 6 only. For set B, you're going to do numbers 1 through 6. For set C, you're going to do numbers 1 and 2. D keeps number 1. And then for the review, let's cross off number 7 and number 11. So that's chapter 8 homework. Now let's get started on chapter 9. So chapter 9 is pretty short. It's a pretty short chapter. So this video won't be too long. It won't be nearly as long as the chapter 8 one. It's talking about correlation, which we talked about in the last video. We talked about how correlation goes from -1 to 1. It measures how strongly or weakly two variables are associated. So we're going to continue looking some about correlation here. First thing I want to look at is how are changes. So if I have daily temperatures, these are daily temperatures for New York from June 2005. And the x and y axis are switched. So the minimum got moved to the maximum and maximum got moved to the minimum when we made this video. Notice the correlation doesn't change because the scatter diagram is just a reflection of itself over this line because the x and y axis changed. So the correlation doesn't change because the scatter diagram is the same, it's spread out the same amount. So our correlation stays the same, and that is R does not change if you switch x and y. R also doesn't change if you multiply or add each x and y value by the same amount. So for example, if we change Fahrenheit into Celsius, R does not change because what's happened to every single x value, we've subtracted 32 and then we've multiplied by 5/9. So we've added by the same amount and we've multiplied by the same amount to every single x value. We subtracted 32 and then we multiplied by 5/9 to get that. I don't know which point that becomes, but to get that point. But one thing you will want to note is the correlation looks stronger if the SVs are smaller. So standard deviations can change size dependent on the variables and on how you change the variables, so if you add or multiply by the same amount. So let's say we have this data versus this data. It is the same data, but I think, if I remember right, all that's happened is this got multiplied by 2 to become that, or something like that. They're the exact same correlation because the spread or the amount between each dot is just a multiplied by a factor of 2. So the spread is bigger, so the standard deviation is bigger, but that spread is multiplied by the same amount, so the standard deviation does not change. So just because one graph is zoomed in or zoomed out, the standard deviation can be changed when you multiply by the same number, but the correlation will not change. So when you look at correlation coefficients, there's a few things you need to know as you're interpreting those correlation coefficients. Remember, the correlation coefficient goes from -1 to 1. It tells you how strong or weak of an association there is. 0.6 does not mean twice as much association as 0.3. That's not what it's saying. R can be misleading if there are outliers, so you can't always trust R, especially if you have something like this, and then there's this outlier here. We know R is going to be a lot smaller than it actually would be without the outlier. R measures linear association, And so if there's an association that's nonlinear, R is not going to work. What that means is you always need to draw the scatter diagram. Because if you have a scatter diagram like this, R is great for it. But if you have a scatter diagram that looks like this, you're going to want to use a parabola, or y equals x squared, for that, because that's the shape it creates. Or an exponential association, something like this. So linear association uses R. If your scatter diagram or scatter plot is not linear, don't use R. Point 8 does not mean 80% of the points are tightly clustered. R is not a percent at all. And it doesn't indicate linearity as well. It doesn't say this is twice as close to a line as this 0.4. So 0.8 is twice as close to a line as 0.4 is. And biggest thing, correlation is not causation, or association is not causation. Just because two things are associated or correlated doesn't mean one causes the other. For example, shoe size and height. As shoe size increases, height also tends to increase. That doesn't mean your shoe size causes your height. There's some genetic factors that cause both of those things. So the correlation coefficient can be misleading in the presence of outliers and nonlinear association. We just talked about that, but just another example. This is linear, but then this outlier right here is going to make the correlation very small, whereas if we get rid of that outlier, the correlation is very big or very strong. And this would be more like a parabola. This shows you what R is if you were to map a straight line through this. If I tried to fit a line through this, it would say the correlation coefficient is 0.02, basically 0, which would look a lot different than this. We'd want to use x squared for that. This one doesn't have a correlation, so you can compare those two. There is definitely a correlation with this thing right here. It's just not a linear correlation. This one has the same, oops, not direct both of those. There's these points right here, are these points right here, but then we add some outliers out here, and suddenly we can draw a line through that data, and that correlation is now significantly bigger than it was before, but it's not accurate. Those outliers are affecting it in an opposite direction from what we normally see. This data is 0.96, it's almost perfect. We throw this in and it becomes 0.8. So those outliers can affect it either way. So when you're dealing with R, a couple things to watch out for on the scatter diagrams are outliers and nonlinear associations. Okay, this question, read through it, choose your answer, pause while you're waiting, and we'll double check and make sure you did it correctly. Okay, you should have chosen B. So what this is saying is, on A, as one variable goes up, so does the other, so that would look like this. That's positive. This is saying, as one variable goes up, the other one goes down. So we start out here at the top and work our way down as we go to the right. That's negative. And then C is just the exact same thing as A, but it's saying as one goes down, so does the other. So it's still positive. Okay, the last thing we're going to talk about with this is ecological correlations. So we talked the other day about how looking at a full average, so for like women's and men's salaries, that can be very misleading versus looking at individual homogeneous groups or groups that have something in common. Similar idea with ecological correlations. What this is, let's just read through this. Sometimes each point on the plot represents the average or rate for a whole group of individuals. So rather than the point representing just each individual themselves, it's taking a whole group of individuals, maybe everybody from the US and then everybody from China and so on, and plotting each average rather than every individual. And so we've got a couple examples of that. The correlation from a plot of averages is called the ecological correlation, and typically ecological correlations are artificially strong, and let me show you what that means. If we have individuals versus averages, all these green dots over here represent individuals versus this represents the average for it. Same for the red and same for the blue. This is a very strong correlation. I would guess that that is like 0.9 versus this one, taking just the individuals rather than the averages, that correlation is probably more like a 0.7. So when I say artificially strong, I mean the average has a lot stronger of a correlation because it's missing that individual variety in between individual people. It's just averaging it. So it's getting rid of all the really low income education levels and all the really high education levels and just going with the middle or the average for each of these. And so we're missing that variety from having individuals. What that means is typically rather than using averages in a graph, you want to use individuals. It's recommended that you stay away from using averages. There's a video you can watch if you want to that goes more into ecological correlation. This is showing the death rate or child survival rate actually in each country based off of how much money that country makes, their survival rate. And you can see the different countries. Each of these dots represents one country. If we take this and blow out, so let's say Saudi Arabia, Sub-Saharan Africa, sorry, I did not read that well. This was the average. We can take it, and then we've got a huge variety. And that's going to create a lot bigger of a football shape than this one. That, whoops, I missed a country. That has a correlation of like 0.9. This has a correlation of like 0.6 or 0.7 there. So we want to look at those individuals to show that there's not as strong of a correlation between how rich the country is versus the child survival rate. There's other factors that go into it. And this blew all of the countries out. You can see there's still a pretty strong correlation, but it's not as strong as the average that we saw a couple slides ago. If you want to watch more about this, you can watch this video, start it at 8 minutes. And the biggest thing from this is just remember association is not causation. There's a few funny examples that you can read there, where in children, shoe size is positively associated with reading ability, which no duh, as children get older, they're going to read better, they're going to be taught how to read, and their shoe size is going to increase. And you can see each of these, and just think to yourself, why would this have an association? What's the behind-the-scenes confounding factor that's going on there? Okay, this is your homework for Chapter 9. Look at that, it was less than 15 minutes for that video. We have shortened this as well. So set A, instead of doing 1 through 7, we're going to do 2 through 6. Set B is just completely gone. Set C, you still have to do all of it. Set D is completely gone. Set E, you still have to do 1 through 5. And review, you still have to do 2 and 8.